Hello everyone, today I am going to review a paper named RCU Usage in the Linux Kernel 18 years later from ACM Operating System Review 2020, Volume 54. This paper provides a compilation of RCU usage over 20 years in Linux kernel, including RCU design, RCU functionality, RCU application, and comparative statistics. Let's start the review. In the past, when programming the concurrent application, the concurrent in kernel level is managed by a single lock provided by Linux kernel, which serializes all execution, creating a bottleneck in lock-extensive programs such as a server application. This approach leading to multiple issues such as locking issue. A single lock can lead to deadlock if we use a poor design. Performance issue. Usually, reading occurs more frequent than writing, and writing has more impact than reading. The single lock treats two kinds of operation with the same priority, which is inefficient. Scalability issue. Single lock serialized operation over multiple cores, which is inefficient. There are many solutions to solve this problem, such as fine-grained lock, a lock that covers a single data. Lock-free data structure that use the different mechanisms to manage the concurrent. Per CPU data structure that share a copy of data among the multiple core. And RCU or read copy update, the advanced paradigm to control the concurrency. RCU is a paradigm that still relies on a lock mechanism, but the weaker one, as it allows multiple readers to read at the same time to reduce the overhead for the read operation, since reading has a lower impact to the system and usually occurs more frequently, while it also provides the capability to write asynchronously. It also guarantees the consistency for the reader over the access lifetime. RCU, as mentioned before, it can satisfy three Linux kernel requirements, which are allow concurrent operation as a basic requirement, use low resource since it needs to be used in the central system, and the last one, provide the deterministic completion time since it works in a critical space in the system. Non-deterministic may lead to timeout or undefined state. These are the design of RCU API, which includes RCU read lock, RCU read unlock, synchronize RCU, call RCU, RCU dereference, RCU assign pointer. This review will not give a detail about implementation technique, but rather provide how should the RCU works in several situations. Let's start with the single read. It is obvious for the single read that data used RCU will provide the data after the reader acquires the lock. For concurrently read, multiple readers can acquire lock at the same time and should be able to access data at the same time. It will start complicated when writer try to write the new value while there is a reader still acquired locks. Back to the property of the RCU that it needs to guarantee data consistency over the access lifetime. After the writer updates data, reader should still get the previous version of the data. Things have more complicated when there are multiple readers read the data and writer try to write the data at the same time. The reader that acquire logs before writer updates data should consistently get the original data, and while the reader that acquires log after the writer update data should consistently get the new version of the data. This diagram shows that RCU ensures data consistency, also provide the correct version no matter how the data change as long as the access session is valid. For the special case when the data is deallocated, for the consistency, RCU should retain the data until the last reader release and prevent any reader to acquire it since it has been deleted. Now we will talking about the application of RCU in Linux kernel over 20 years. It became a critical part and improved efficiency of the kernel a lot during past 20 years. The wait for completion pattern is a fundamental aspect of the RCU, designed to ensure that all ongoing activities, especially those within RCU read site critical section, are completed before certain actions are taken. In this pattern, we have two roles: the waiter who need to wait for the completion of the activity and the waitee who are performing this activity. Waiters use functions like synchronize RCU for synchronous waiting or call RCU for asynchronous waiting. A practical example of this pattern is found in Linux NMI system. Here RCU is utilized to safely unregister NMI handler. The benefits of using RCU in this context are: it ensures high performance by avoiding cache miss on the other CPUs, also provided deterministic execution times for entering and exiting critical sections, and enable dynamic handling of NMI handler without the deadlock risk associated with traditional logging mechanism. The use of RCU as the substitute of the traditional reference counting enhance the performance and efficiency. In traditional system, reference counting often involve atomic increment or decrement operation, which can be resource intensive and slow, especially in highly concurrent environments. RCU changed this dynamic by allowing thread to hold the reference to the data item within RCU read site critical section. This method eliminates the need of explicit counting, memory barrier, or atomic operation in the data item usage path, leading to much faster and more efficient process. The key advantage of using RCU in this context is dramatically reduction in overhead. For instance, in a CPU-bound loop, switching from atomic increment and decrement operation to empty RCU critical section can result in performance improvement ranging from an order of magnitude on a single core to a several order of magnitude on system with numerous cores. The application of this reference count is used in IP stack. Instead of counting the number of processes that use the IP, they only use log to hold the reference instead of increment or decrement the number. The context of type-safe memory is an innovative approach to manage the memory, particularly in the log-free algorithms. This concept is crucial for ensuring the memory retains its type even after it has been deallocated, thus preventing its immediate reuse for the different purposes. A notable example of type-safe memory in action is the reverse page map in the Linux virtual memory system. The page memory retains its type after it has been deallocated. It remains the same type until the last RCU releases the lock. The advantage of using this approach are it simplifies the memory reclamation process in concurrent systems, making it safer and more reliable. Secondly, it significantly reduces the overhead associated with traditional memory reclamation techniques, particularly in systems with high level of concurrency. This approach ensures that memory management in complex systems like the Linux kernel is both efficient and error resistant. The RCU publish and subscribe pattern efficiently manage data synchronization. The data is published using RCU assign pointer for atomic updates and subscribed via RCU dereference for lock-free read, ensuring consistent access. This method is crucial for data integrity and system stability. The example usage of this approach is a system called table in PowerPC system. Using RCU instead of traditional read-write lock is an efficient approach since it has a lower overhead and allows multiple reads, and it also can prevent the deadlock. Linux PID hash table synchronization uses this approach. However, because of paradigm shifting of the code, it is not universal conversible. RCU itself offers fast paths for read-heavy operation with a minimal contention, enhancing concurrency and reducing synchronization overhead. In the other hand, slow paths available for write operation, ensuring data consistency but with more synchronization. An example is the per CPU read-write semaphore in the Linux kernel. It balances read and write performance. This approach significantly boosts the read efficiency in read-dominant systems, improving scalability and demonstrating RCU's versatility in handling concurrent operation. But one biggest concerning point of RCU is it not force mutual exclusion, which is only either one reader or writer can access at the same time, so it cannot completely be a substitute. Hence, there are many algorithms that use RCU apply the new technique to solve the problem. Imagine a big data structure. While we update each member, it might have a multiple readers read the data while the update is incomplete, which lead to partially updated data. Here we change the RCU instead of protect the structure, change to protect the pointer, point to the data structure. This approach will ensure atomicity to the data. The showing diagram illustrates the partially update occur when some reader read while update is not finished. This one is the solution. Pointing to data structure and update is more secure and consistent. Marking obsolete object is a key technique for maintaining data integrity in concurrent environments. This method tags objects as outdated upon update or removal, preventing concurrent reader from accessing stale data. A notable use is in System VIPC for handling semaphore, ensuring data remain valid even during concurrent modification. This approach effectively manages simultaneous read and write, maintaining consistent and correct data view across the thread and process. is particularly valuable in RCU system for ensuring non-blocking, safe read operation, highlighting RCU's adaptability in high-performance multithread contexts. Retry reader is an approach handle the scenario where the reader encounters update or obsolete data. Instead of discard or raise the error, reader retry reading if they have detected any data change during the access. This approach is very useful in path lookup in virtual file system, since it ensures data correctness over the update of data. For the usage statistic, RCU has adopted to the Linux kernel over 16,000 within 20 years. It is because of its versatility and efficiency. In terms of implementation, Internet Relay Module has highest usage percentage, since the Internet Module is high concurrent, resource extensive, and reliability critical system. It outlines the performance of RCU. For the conclusion, RCU is a very versatile concurrent management mechanism that proven to be a game changer over 20 years. It redefined the traditional paradigm of concurrent management and has been adopted to many applications nowadays. The performance of RCU opens many possibilities in high concurrent systems and make it ready for the modern computing challenge. Thank you for watching.